So another look at Hess's law. Remember that Hess's law states that the enthalpy change for a reaction is independent of the route taken. So as we saw with the enthalpy of formation problems, we can plot an alternative route that links reactants to products via, in that case it was elements, then and we have numbers for the arrows, then we can navigate our way, bearing in mind that we have to flip the sign on any enthalpy changes if we're navigating in the opposite direction to the way that the arrow is pointing once we've built our cycle. So only one worked example for you here, then the rest is open to you to practice. Here's the question. What I'd like you to do first, ideally, is have a go by yourself, see what you can come up with, then continue to watch the video, see what I do, see where you went wrong if you did, and so forth. Okay, there's only going to be one worked example in this video. So there it is. You can see the question. If you read it carefully enough, you'll recognize that the equation they want us to actually get delta H for is this second one, which actually is a formation enthalpy. It's the enthalpy of formation of C4H4O4 maleic acid. They're giving us this bit of information here. I think that's basically just telling us what you should be able to work out for yourself, really, which is that the enthalpy of combustion of C4H4O4, the equation would be represented as such. There's the complete combustion, all the carbon ends up as CO2, all the hydrogen ends up as water. That's the only option for hydrogen. I think they're just making sure you got that before you take it into the next step. So have a go, see what you can come up with, and then we'll see how close you got. So I'm going to move on straight away now to going through the answer. Pause it if you still need to. Here we go. Now, first thing to think about then, we've got three equations here. We've been given three data. This time they're enthalpy of combustion data. So we know the definition for that. The enthalpy change when 1 mole of one of those chemicals is completely burned in oxygen with everything in its standard state. So C4H4O4, we're told it's a solid in the question. Complete combustion, that's the one we've already given in the question itself. Complete combustion of carbon. Apparently it's exothermic, 393.5 kilojoules of heat released for every mole of carbon that burns. That'd be just carbon plus oxygen makes CO2. And similar, a certain amount of heat released for every mole of hydrogen that's completely combusted, which must mean making H2O. Standard state, so it's H2O liquid. Anyway, now let's see how we can get a cycle out of all of this then. So 1 mole of a substance is an important bit in this, as we're about to see. Well, there's the calculation, sorry, there's the equation from the question that we need to get delta H for. And as it goes, yeah, we could label that as delta HF of C4H4O4 because it's 1 mole of that chemical being formed from its elements. So great, we can stick a label on it. Anyway, the real objective here is to make use of the delta H combustion numbers. Definition again, 1 mole of a substance completely burned in oxygen. We're talking about burning something. We're talking about burning carbon, hydrogen, maleic acid. We'll have to think about the oxygen as well, how that fits in. Basically, the thing that we need this time, it was elements before, but this time we're dealing with delta HC. But the other bit we need in this triangle would be combustion products. We need to have an arrow. Well, we need to have CO2 on here somewhere because we're going to have carbon turning into CO2. The carbon's in C4H4O4 turning into CO2. Likewise H2O for the hydrogen atoms that are involved. So we're going to need combustion products. So let's put carbon dioxide and water in first because I've got here carbon and hydrogen, and when they combust they'll make carbon dioxide and water. The idea will be that then we could draw arrows from each of the substances that can be combusted to carbon dioxide and water. There they are. And then if we put numbers on those arrows, then we're good. So before we had the arrows pointing upwards because the definition was 1 mole of a substance formed from its elements. So the arrow went from elements to the substance. Here it's 1 mole of a substance being combusted. So they go from the chemical being combusted, that's a reactant in that process, to the combustion products. It totally balances. Remember, it's a three-way balanced equation, so you don't have to. There's not 8 carbons here. There are 4. There's 4 carbons here, 4 carbons there, 4 carbons there, and so on for the other 2 elements as well. So it's a three-way balanced equation. Now, why haven't I put an arrow coming off the O2? Well, I could say by definition again, but that doesn't really follow here. That is essentially what we would say if we had to. You can't burn oxygen. Oxygen isn't a fuel. Carbon can burn, hydrogen can burn, maleic acid can burn. We know lots of substances that will burn. And burning, the fire triangle, yeah, and here we have the Hess triangle. Burning is fuel, oxygen, and heat. So heat's basically activation energy. oxygen and fuel. That's the oxidant and the substance that's going to be oxidized. So yeah, that's the idea. Oxygen isn't a fuel. You can't burn oxygen. What would you make? Oxygen oxide? Doesn't really make sense, does it? So we just ignore oxygen in combustion Hess cycle problems. 1 mole of a substance being completely combusted, so burning a mole of carbon would give us 393.5 kilojoules per mole, kilojoules of heat released. We've got 4 moles of carbon, so when we take that number there for the arrow, we're going to have to just quadruple it. We're going in the direction of this arrow, as you'll see in a sec. We're going to navigate the cycle from here to maleic acid via combustion products. And in this case, we're actually going to be going with those arrows. Last time we were going against them, but this is different. 2 hydrogens, so that's 2 moles of hydrogen, we read that as here. So 1 mole of a substance being completely burned, 1 mole of hydrogen minus 285.8, 2 moles, double it. We've already said about the oxygen, the enthalpy of combustion for oxygen is non-existent because you can't burn the stuff. So that leaves us with just the enthalpy of combustion of maleic acid. It makes sense that the arrow points downwards because we're talking about 1 mole of maleic acid turning into carbon dioxide and water. It's exothermic because it's combustion of a hydrocarbon or of anything, and so it's minus 1356, just taking those numbers straight out of the table. So this time again, we're going to navigate the cycle. What we want is the delta H for this top line equation: 4 carbons, 2 hydrogens, 2 oxygens. How much heat energy change would there be? What heat energy change would there be if those elements formed 1 mole of maleic acid? So we're going to imagine carbon and hydrogen burning in those proportions, 4 and 2. Then we're going to imagine, and again, remember this is totally hypothetical, but we're going to imagine like the complete opposite of burning, so the unburning. Yeah, we talked about the anti-formation in the previous video, the unburning of maleic acid. So how much heat energy would be taken in when CO2 and H2O turn back into maleic acid? And the answer is, well, however much was released, it's going to be that same amount taken back in. So the delta H for our problem here, 4 CO2 plus 2 H2O, makes C4H4O4 is going to be plus 1356. We're just going in the opposite direction to what the arrow represents. It's combustion, it's exothermic, so uncombustion, such a thing existed, it's going to be endothermic by exactly the same quantity. So let's put our numbers into a cycle. Remember, we must always show an unsubstituted expression first. You'll get away with actually not drawing the cycle, provided that you show that string. But if you don't show the string and you don't show the cycle, then you just don't get a mark. That's as simple as that. So 4 enthalpy of combustions of carbon, add to that 2 enthalpy of combustions of water. Those are both negative numbers, so we're adding negative numbers, that's fine. And then subtract, because we're going in the opposite direction to the arrow, so the opposite of combustion, so the anti-combustion of 1 mole of maleic acid. So subtract that value, which means subtracting a negative number. Put the numbers in. So I've solved the sort of multiplications there, the 4 times and the 2 times, and what we get is exothermic, this time minus 789.6 kilojoules per mole. So that's the delta H for the enthalpy of formation of maleic acid. Now think about it, that formation there is not an example of is not a reaction that would actually happen. If we put carbon, hydrogen, and oxygen together and ignited it, we'd probably just get CO2 and H2O. We wouldn't get the formation of a substance like that necessarily. Or if we did, there's no guarantee it'd be C4H4O4. So here's a way of us getting a enthalpy of formation for something from potentially real values, because burning in particular is pretty easy to manage and to do and to achieve, therefore, sort of temperature measurements and calorimetry for. So we could set fire to some carbon, some hydrogen, some maleic acid in very controlled conditions, and we could actually get delta H values and then get this desirable sort of enthalpy of formation that might tell us something about the stability of that possibly. So there's your one worked example. Hopefully you can see what to do. You've obviously got the experience of using enthalpy of formation data already. This is a similar exercise, but you have to think about which way the arrows are pointing. Let's just have a quick look at 1 or 2 other small things then. So if it helps, we could say that in general, this time we're dealing with delta HCs rather than delta HFs, we've always got this situation where all the arrows are pointing down from the reactants and the products of the equation that we're trying to get delta H for to the combustion products. So when we navigate from reactants to products, which is usually the direction we'd be going in, we're going to go with the enthalpy of combustions of reactants, so we'd add them, and then we're going against, so the total reverse of burning or of combustion, the combustions of the product. So we'd subtract those values, we'd flip the sign on them and add them basically. Anyway, so you get reactants minus products this time if you wanted the general formula for it. I've just realised another typo. I thought I'd got these typos out. I'm not doing very well today. Those should say delta HC, shouldn't it? Okay, I'm sorry about that, guys. The sum of the enthalpies of combustion of the reactants, subtract these sums of the enthalpies of combustion of the products. Products minus reactants for formation, reactants minus products for combustion. Oopsie daisy. Just another quick thing to think about. Now that we've seen enthalpy of formation and combustion a bit more, it's worth just noting a few things here. Delta H is just that difference in energy between start and finish, endo or exothermic either way. The labels that we put on delta HC and delta HF are just a bit of an academic exercise, really. So what labels could we put on that hydrogen plus oxygen equation? Well, that's the enthalpy of formation of water, because we've got there 1 mole of water being formed from its elements, hydrogen, oxygen, obviously both elements. But also we've got 1 mole of a substance being burned in oxygen here. We've got 1 mole of hydrogen being combusted. So it's both. So they're the same value. There's one difference between H2 and half an O2 and a H2O in those states. But we could put two different labels on, and they're the same number. So there's no difference between the enthalpy of combustion of hydrogen and the enthalpy of formation of water. Basically, anytime we're combusting an element, so that really limits our options. It's hydrogen or it's carbon or it's sulfur, perhaps. Okay, there aren't many combustible elements. Well, okay, they're all the metals as well, to be fair, now I think about it. But we'd expect there to often be this kind of dichotomy of its combustion and its formation. It's combustion of the element, it's formation of the combustion product, but only if we're talking in terms of 1 mole of. So 1 hydrogen becomes 1 H2O, 1 carbon becomes 1 CO2. So it works in these examples here. It wouldn't work if it was like aluminium becomes aluminium oxide, because there's like 2 aluminiums and 1 aluminium oxide. But anyway, I've purposefully didn't put an example like that up. Similar here then, we've got there the enthalpy of combustion of carbon, because we've got 1 mole of substance being completely burned in oxygen, carbon, and also it forms 1 mole of a substance from elements. So as I said, whenever you're combusting an element, have a quick look. It might be that you could label it delta HC of that element, because you've got a mole of it. And if in the balanced equation it forms 1 mole of product, oxidation product, then it's the formation of that product from elements, because the thing you burnt was an element. So I just wanted to point that out. These labels are pretty versatile. Here we've got one equation with 2 labels, and we've got 2 examples like that. So there you go. That's it for now. There's more practice questions on the classroom to help you with this.